share the screen. Okay, so how many students are here? 3 students are here. Okay, well, we're going to start because our time has started. So last time we were doing particle in a box and we were talking about expectation values and how many students are here? 3 students? Okay, now 7 students are here. Okay. So we were doing particle in a box and we were talking about expectation values and momentum. We're still on quantum mechanics chapter, okay? And hopefully we'll finish this in 1 or 2 days. I think by tomorrow we should finish quantum mechanics, or maybe even today we'll finish it. So then we will move on to our next chapter, which is atomic structure, okay? And so last time we were doing this example on expectation value of the position of a particle trapped in a box L wide. So we found the expectation value of the position operator, which is the integral of from minus infinity to infinity x times psi whole magnitude square dx. Okay, one thing I want to mention in the midterm, that many of you made this mistake in the midterm, okay? That probability has to be psi whole magnitude squared, and some of you just took psi, the integral of psi, and I was very surprised why that happened, because remember I said over here that a probability is the integral from certain regions, whatever regions that over which you're trying to find the probability, and it is psi whole magnitude square dx. So you have to take the probability from, you have to take psi whole magnitude square, and because I said that psi was a cos square x, it would have become a power 4 cos power 4 x, and then you had to expand that using the identity I gave you. Many of you made that mistake that you did not take psi whole magnitude squared, okay? So next time I hope you don't make that same mistake again. So so last time what we were doing is that we were finding the expectation value x of the position of a particle trapped in a box L wide. So this is how we do this, is that we take the integration from minus infinity to infinity x, which is the operator, like I gave you the values of the operators as well, ठीक है? ऑपरेटर्स की क्या वैल्यूज होती हैं, यहाँ पे पोजीशन x है तो उसकी ऑपरेटर x है, मोमेंटम p है, उसका है ऑपरेटर h bar over I del by del x. The expectation value of the position operator is quite easy to find actually. Where was it? Where did it go? Expectation value of the position operator is very easy to find because you just have to take the integration with respect to x, okay? I cannot find it right now over here. But anyway, so our task for today, we did last time, we also did an example. Yeah, here. We did this example, okay? And where we use, what is the psi that we're using here? The psi that we're using here is the psi for a particle trapped in a box, which is, as we mentioned last time, that psi is, this is the particle in a box, the psi for a particle in a box, which is square root 2 over L sine and pi x over L. ये सबको पता है ना? So now what we want to do is we want to find the expectation value of the momentum. And what do we mean by expectation value? What we mean by expectation value is the average value of that operator or whatever that observable is, okay? So average value of the momentum, we will get a strange result here. We will get, I will show you that it becomes 0, okay? Which we do not, with the average value of the momentum is coming 0, but what does that mean? I mean, I'll show you how we get 0 first, and then I will tell you what that actually means. So finding the momentum of a particle trapped in a one-dimensional box is not as straightforward as finding the expectation value of the position of a particle. Okay? So psi in our case is, we know that it's square root 2 over L sine n pi x over L. And then d psi by dx, if you take the derivative of this function, what will that be? You just have to take this n pi over L, multiply it, and then switch this cos to the sine. Sine to the cos. Then we will get that's our d psi by dx. And why are we trying to find d psi by dx? Because we know that if we have momentum function, if we want to find the expectation value of the momentum, we will take the integration from minus infinity to infinity, psi conjugate. Psi, in this case, what is the conjugate of psi? It will be itself because there's no iota in this r psi function. So the conjugate will be itself, okay? So conjugate is equals to psi n is equals to square root 2 over L sine n pi x over L, okay? So so the expectation value of the momentum operator is the integral from minus infinity to infinity psi conjugate. Then we have p hat psi times dx, okay? Is what will that be equal to? That will be equal to psi conjugate, the integration of psi conjugate, and then we have to put the value of we have to put the operator p in here, ठीक है? यहाँ पे h bar over I d by dx हो जाएगा applied to psi. So when you apply that to psi, that's where we found d psi by dx before, ठीक है? So it will give you h bar over I, ये बाहर आ जाएगा, ये d psi by dx ये है हमारे पास, तो ये हमने इसमें डाल दिया. एंड इसमें फिर ये इक्वेशन हमने इसमें डाला है, ये भी डाला है बिकॉज दिस इज psi conjugate एंड दिस इज d psi by dx. ये दोनों हमने इसमें डाल दिए हैं, ठीक है? इसकी जगह हमने ये इक्वेशन डाला है और इसकी जगह d psi by dx की जगह हमने ये डाल दिया है. तो वी गेट दिस इक्वेशन नाउ. ये सबको समझ में आ गया ये इक्वेशन किस तरह से आया है? ये इक्वेशन, दिस इज द एक्सपेक्टेशन वैल्यू ऑफ द मोमेंटम. And then because we have sine ax cos ax, where we can write a as n pi over L. So the identity is that if we have an integration sine ax cos ax dx, that will give us, this is an identity, ठीक है? ये हम use करेंगे इसमें 1 over 2a sine square ax. तो इसको हम जब use करेंगे इसमें 1 over 2a sine square ax, तो जब हम इसमें use करेंगे we will get h bar over I, h bar over I L, and this we'll get ये जो a है ना 2a से हम divide करेंगे and a is n pi over L. ये बस mathematics से थोड़ी सी algebra है, आपको करनी पड़ेगी. लेकिन h bar over I इसकी जगह हम डालेंगे 1 over 2 n pi over L. n pi over L cancel हो जाएगा, 2 cancel हो जाएगा, it'll be h bar over I L and sine square n pi x over L, and the whole taking from the limits from 0 to L is equals to what? So now we have to solve this expectation value of momentum. As you know that if n is equals to 1, it will be sine square pi x over L, ठीक है? और यहाँ पे L भी डालेंगे और 0 भी डालेंगे. 0 डालेंगे तो वो 0 हो जाएगा, L डालेंगे तो L cancel हो जाएगा, it'll be sine square n pi. तो n pi sine square n pi, as we know that, as what do we know about sine function? What do we know about the sine function? So the sine function goes like this, ठीक है? So every time, if it's 0 pi, it will be here. If it's 1 pi, it will be here. If it's 2 pi, it will be here onwards, ठीक है? Onwards, जो भी होगा. So whenever it is a multiple of pi with n is an integer, it will always be, the sine function will always go to 0. So we're getting expectation value momentum is 0. So why is this an interesting result? Can anyone tell me why is this an interesting result that the expectation value of momentum is 0? It's interesting to us because the particle's momentum on average is 0. How we can interpret this is that the particle will have, because obviously momentum is a vector now. It has direction because it's equal to mv, where v is the velocity of the particle. So the velocity obviously has direction. So in that case, like either half of the time the particle can be moving in one direction, half of the time in another direction. So they will cancel out. So the expectation value in one direction will cancel out with the expectation value in another direction. So basically now we have to figure out what are those values of the momentum, that positive and negative values of those momentum, okay? So that's what we're trying to figure out. Any questions so far? No? Okay, so at first glance, its conclusion seems strange. But if we know that E is equals to P squared over 2m, that will be the energy in the particle in the box, right? Isn't that what we said before? The energy in the particle in the box is En is equals to n squared pi squared h bar squared over 2ml squared. Okay? So that was for the energy in the particle in the box. So then here, what are we saying now? Here what we're saying is that E is equals to the kinetic energy is equals to P square over 2m, and particle in a box was defined in such a way that it has kinetic energy, the particle has kinetic energy, but does not have potential energy, right? Because we're saying that the potential energy inside the box is 0. So we're saying that the total energy of the particle is the kinetic energy, which is P square over 2m. So if you rearrange this, it will become P is equals to, and why did I write n now? Because, okay, if we rearrange this formula, it will become P is equals to square root 2me, right? But because we had energies, which is what? Our energies were, where did it go? Always gets lost. The energy is equals to n square pi square h bar square over 2 ml square, right? If you all remember that correctly, here we go. Slide 34. N square pi square h bar square over 2 ml squared. So when we put that in here, it will be in terms of n. That's why we have to write Pn as well. Momentum is a function of n. Okay, so it will be plus minus because when you take the square root, it will become plus and minus. So plus minus n pi h bar over L. ये किस तरह से हमारे पास ये आया है ये number? Because 2me, because what we have here is P is equals to plus minus square root 2me, right? 2m en Pn. So now we will put the values of the energy in here. So what will that become? 2m n squared pi squared. You just have to do some algebra here, okay? H bar squared over 2ml squared. 2ml squared, right? तो इससे हम करेंगे तो ये m 2m और ये 2m कैंसिल हो जाएगा, बाकी हमारे पास क्या बच जाएगा? प्लस माइनस n pi h bar over L, right? So this is what we get now, n pi h bar over L plus minus. So what does this indicate? This indicates that the particle is moving back and forth and the average momentum for any value. So if you take the average of these two values, you will get half of the time it's going to move in the positive direction, and like expectation value is the average. So approximately average में क्या होता है कि if you take the average of the momentum, it will be half of the time it will move in the positive direction, half of the time it will move in the negative direction. So if you take the average of those two, it will just be 0. So that is the expectation value of the momentum. And so we can also, according to equation 5.47 here, is it making sense to everyone? So according to 5.47, which is this equation over here, there should be two momentum eigenfunctions. Now we talked about eigenvalues and eigenfunctions and eigenvalues, okay? So if you have a momentum operator here applied onto psi, will give you the momentum, the value of the momentum and psi, okay? And here we have to apply the function of momentum, okay? That will be here we will apply h bar over I del psi by del psi by del x is equals to, you will get some value for momentum and psi, okay? So we want to solve this eigenvector eigenvalue equation, and how we will solve this is that we want that when we apply momentum operator onto psi, it should give us some value and then it should give us psi back. So how will we solve this? That we want to solve, there should be two momentum eigenfunctions for every energy eigenfunction correspond to two possible directions of motions. Okay? So now basically what we have said is that the average value of momentum is 0. Average value of the momentum is 0. So what can we conclude from that is that half of the time it moves in one direction, half of the time it moves in another direction. But now what we want is that for those two, now we're saying that when we have a, what do you mean by eigenfunction eigenvalue equation. This is the P, this is the operator here, this is the function, eigenfunction, and this is the eigenvalue, and this is the eigenfunction. Okay? What this means is that when you apply P operator to psi, you will get some values times psi. Okay? And those values are the values that the momentum will take. So Pn is a real number. Okay? So we're trying to find out now what are these eigenvalues that correspond to the eigenfunctions Pn. Okay? So now let's see what we will get. The equation holds only when the wave functions are, we know that P operator is h bar over I del by del x. Okay? And we know that this is our psi of n. Psi of n हमें पता है और P operator भी हमें पता है. लेकिन हमारे पास कुछ मसला आ रहा है यहाँ पे कि अगर P operator ये है applied onto psi of n, psi n, then we get, when we take the derivative of this function, what will we get? We'll get h bar over I still will remain the same. H bar over I will still remain the same. But d by dx times this thing will be what? N pi over L multiply कर देंगे, यहाँ पे square root 2 over L भी multiply कर देंगे, ये sin N pi x over L will become cos N pi x over L. ठीक है? So when we look at this equation, so h bar over I times d by dx of this thing of psi is giving us something else which is not a function of, which is not in terms of sine itself. Like if I write an equation, you're all understanding that if I write here P hat psi n to be an eigenvalue, if this is an eigenvalue, say, you must have all studied linear algebra before as well, right? This equation has to be satisfied, ठीक है? मतलब कि यहाँ पे हमारे पास क्या आएगा? Pn psi n, Pn psi n, ठीक है? This equation has to be satisfied. मतलब कि when I apply the operator here, h bar over I del psi by del x, it should give me some value which is Pn in this case, times psi itself. And what is our psi? Psi is square root 2 over L sine n pi x over L. ये समझ में आ रहा है सबको कि हम क्या करना चाह रहे हैं यहाँ पे? We want it to be some function, some value times this psi n itself. ठीक है? This is psi n. This is psi n. So in order for it to be applicable to the eigenvalue, eigenfunction equation, it has to be a function of psi n. However, that is not what we are getting, ठीक है? That is not what we're getting, because when we take the derivative of the sine function, it will turn into a cos function. So this is not an eigenvalue, eigenfunction equation. So what we want to do is basically what we're saying here is that these are not the energy eigenfunctions. This is not the energy eigenfunction. Why? Because when we take the derivative, this is not the momentum. This is not the eigenfunction of the momentum operator, of the momentum eigenvalue eigenfunction equation, because when we apply the momentum operator onto this eigenfunction, we do not get the same eigenfunction back. It's not some number Pn times psi of n. So we want to find the correct momentum eigenfunction. So how can we do that? So let's see how is यहाँ तक सबको समझ में आ रहा है? Any questions?
मैम नो क्वेश्चन तकरीबन समझ आ गया.
Okay, good. Okay, then to find हाँ?
मैम डिवाइड कर लें बोथ साइड psi n की वैल्यू.
डिवाइड क्यों करेंगे हम?
Pn आ जाएगा फिर नहीं आएगा?
डिवाइड तो टेंजेंट डिवाइड करेंगे psi n के साथ, तो ये तो साइन कैंसिल हो जाएगा, यहाँ पे कोटेंजेंट आ जाएगा. नहीं, हम साइन डिवाइड नहीं कर सकते ऐसे ही. So हम ऐसे, we want to find another method by which we can find the momentum eigenfunctions. ठीक है? हाँ? Okay, so anyway, sine theta, now we know that sine theta is equals to e I theta. We have this identity, okay? Sine theta in terms of exponential of these exponential of I theta minus minus I theta over 2i. ये identity हमारे पास है, ठीक है? इस 2i को इससे divide कर दें, इससे divide कर दें, हमारे पास ये आ जाता है. Now what we're doing is that we want to apply a trick over here, ठीक है? कि we know that the momentum has two values, ठीक है? अभी हमने कहा था कि momentum operator को हम अगर apply करें, then we do not get this eigenfunction again. So we have to find maybe eigenfunction can be written as a linear combination of two other eigenfunctions. ऐसे भी हो सकता है ना? And why? Because we have two values of momentum. हमने अभी तो कहा था कि average value of momentum 0 आ रहा है because we have two different values of the momentum. One is a plus and one is a minus. So these are two other values that we're getting. The average of the positive directions and the average of the negative directions. So what we can do now? So what we can do now is that if we write this sine n pi x over L in terms of this expanded using this identity, then in our case theta is n pi x over L. Okay, so it will be e power I n x over L. And e power minus ix over L with 1 over 2i divided by that because we did it over here. And then square root 2 over L तो हम फिर भी multiply करेंगे क्योंकि वो हमारे psi n में आ रहा था ना coefficient. Psi n was square root 2 over L sine n pi x over L. Make sense? तो इसकी जगह हम उसको लिख लेते हैं, इस sin n pi x over L की जगह हम ये terms लेंगे. So basically we can now write psi as a linear combination of these two sides. यहाँ तक समझ में आ रहा है सबको? Or you want me to explain on the board? Basically what we're saying here is that psi n is equals to what? Square root 2 over L sine n pi x over L, right? N pi x over L. And we can write this as square root 2 over L 1 over 2i, because we have this term, right? E power I n pi x over L. इस तरह से लिख सकते हैं ना हम? Minus 1 over 2L 1 over 2i e power minus I n pi x over L. ऐसे लिख सकते हैं ना हम? Because of this identity that we have over here, trigonometric equation, we can write our psi as a linear combination of these two psi's, which is basically this equation here. This equation psi n can be written as a linear combination, and this first term, ये जो हमारे पास first term आ रहा है, इसको हम कहेंगे 1 over 2i square root 2 over L e power जो भी whatever the value is, ठीक है, plus minus 1 over 2i, ठीक है, या इसको बस माइनस ही कर देते हैं यहाँ पे, minus 1 over 2i e power जो भी है minus of this whole thing, ठीक है. So and wait, there's a square root 2 over L here as well. यहाँ पे square root 2 over L भी है, ठीक है. So you understand how we can write this psi and can be written as a linear combination. अब इसको हम कहेंगे, इस term को हम कहेंगे psi n positive, और इसको हम कहेंगे psi n negative, ठीक है. So basically we can write psi n as a linear combination of psi n positive and psi n negative. Okay? So now let's check if we will get the if it satisfies, if in these individually will satisfy the eigenvalue equation. So now let's see. Now we have this equation p hat psi n. Now before we used psi n, psi n, which was this one, and this did not satisfy the eigenvalue equation. So now we will use psi n positive, and then we will use psi n negative, and we will check that if they satisfy the eigenvector equation. So now इसमें हम डालेंगे h bar over I d by dx psi n positive. Psi n positive हमारे पास ये आया है, ठीक है, ये हमारे पास psi n positive. तो h bar over I times 1 over I square root 2 over L. इसका derivative क्या होगा अब? N pi x I n pi over L times the same thing again, exponential term back. So when you simplify this term and then write it back, can it be written in terms of this again? Is everyone following what I'm saying here? ये जो हमारे पास आया है h bar over I d by dx psi n, ये जो हमारे पास आया है, this is h bar over I times d by dx, derivative of this term, of this psi n. When we wrote it in this term now, in this form, it can be rewritten back in terms of psi n positive. Because if you can see 1 over 2i, 2 square root 2 over L, and this term will give you back n pi h bar over L psi n positive. Yes? And this is the Pn positive we said before. This is exactly the P sub n positive that we said before. Yes? Isn't this making sense now? So basically we're saying that the Pn positive is equals to positive n pi h bar over L. So ये जो हमारे पास eigen functions आए हैं, ये ठीक आए हैं, ठीक है? And they correspond with the positive and the negative value of the momentum, the negative and positive values of the momentum. Okay? And so if we apply p hat onto psi n positive, we get pn positive, psi n positive. Okay? Then we will get h bar over I d by dx psi n positive is equals to, we apply the same procedure again that we just did over here. And we get now pn यहाँ पे I think I repeated this again. Similar, okay, yeah, this is the same one again. And then when you do the same procedure again for psi and negative, there will just be an extra minus sign, okay? So it will become n pi h bar over minus n pi h bar over L. यहाँ तक सबको समझ में आ गया? So basically what we're saying here is that one thing we have said here today is that the expectation value of the momentum is 0, and that's because half of the time it's moving in the positive direction, half of the time it's moving in the negative direction. That's why the expectation value is 0. And then we have also said that we want to be able to solve the eigenvalue equation for the momentum, and this psi n that we calculated for the particle in a box does not satisfy the eigenvalue equation, because when we take the derivative of the psi n with respect to x, we get something as cos, because the derivative of sine is cosine function. So that does not satisfy the eigenvector equation. And in order to find the size that do satisfy, we write the sine theta in terms of the exponentials. And then when we take the derivative, when we put in psi n positive, so then we can write psi n as a linear combination of the psi n positive and the psi n negative as a linear combination, okay? As I did on this in this board over here, okay? Because the sine theta can be written as 1 over 2i e power theta I theta minus 1 over 2i e power minus I theta. Okay? So then when you solve for the eigenvector, we want to see if these two sides satisfy the eigenvector equation. So when we put this h bar over I d psi by dx, psi n positive for this psi then it satisfies this eigenvalue eigenvector equation with a Pn, which is our n pi h bar over L, which is according to what we predicted before. These values of momentum, these two expectation values of momentum, these two average values of momentum in the positive and negative direction are correct. Okay? And then we did the same thing for the negative direction for psi n minus. For psi n minus, if we do the same procedure for that, we will get Pn minus is equals to minus n pi h bar over L. Okay, so these are the momentum eigenfunctions, momentum eigenvalues, this one and this one, that correspond to the eigenfunctions, this psi n positive and psi n negative. यहाँ तक समझ में आ गया सबको? Any questions so far? No questions? Okay, then we'll move on to the new PowerPoint. The new PowerPoint was, we're going to, I guess we'll be able to finish quantum mechanics today, hopefully. Okay? So, are there any questions related to anything related to quantum mechanics we have studied so far? No? Okay, then we'll continue. And I was wondering, why did a lot of students have problem with the midterm? Was it too difficult or something? Like, I was like, some students had expected more from, didn't get as well as I thought they should get. But the biggest problem that I noticed was that in question number 1, it was psi. I wanted you all to use psi whole rounded square, but most of you used just psi, the integration of just psi. So that was a big problem. Anyway, let us continue with with our topic. So of quantum mechanics, and I guess we'll be able to finish quantum mechanics today, hopefully. Okay. So now the previous put particle in a box that we were talking about, the particle in a box, this one. The one that we talked about before, this is called an infinite square well. Did I mention this last time, that why is it called an infinite square well? It's called an infinite square well because the potential energy goes to infinity as infinity outside the box. Outside the box, and the box, it goes to infinity in a sense that the particle will be the potential energy outside the box. So I will talk about, I will erase a board here. There are two different things we can talk about. The infinite square well, which looks something like this, ठीक है? यहाँ पे L है, यहाँ पे 0 है. Or outside the box, ठीक है? The potential energy U is 0, infinity here. And the potential energy here is also infinity. This we already discussed before, ठीक है? And inside the box, the potential energy is what? 0. So the particle will be trapped inside the box. This is the particle. It will be trapped to move only inside the box. Okay? Now we will be talking about a finite potential well. Okay? A finite potential well looks something like this. If you can see this diagram over here, finite potential well looks something like this. Okay? Looks something like this. Okay? What is happening in the finite potential well? Shows a potential well with square corners where U is high and L wide. Okay? So we have 0 to L. What's happening inside this regions 1 and 3? We have potential energy U. Okay? And here we have a potential energy 0. Wait a minute. Let me just double check this. Yeah. So inside the well, the finite potential well is such that inside the well, we here for regions I and 3, the energy of the well is U. As you can see over here, U is the energy of the well. And in the region 0 to L, the energy is what? 0, right? So the finite potential well can be defined like this, okay? And we call it finite because nothing is going to infinity here, ठीक है? इसको हम infinite square well कहते थे, infinite square well. Infinite square well because it was going to infinity, ठीक है? यहाँ पे हम इसको finite square well कहेंगे. And these are very important in quantum mechanics, ठीक है? The finite square well and finite square well. You'll be going into these in more detail when you study the course on quantum mechanics, ठीक है? Which you will be doing next year. But next semester you'll be studying that, ठीक है? And then here the energy is U. The energy is U here. And from 0 to L, the energy is 0. The potential energy is 0, ठीक है? If this is a graph of energy versus position, ठीक है? Oops. This is a graph of energy versus position. So here is we're plotting energy. So in this region, which is going to from 0 to minus infinity, it will be energy is U. And in this region, which is going from L to positive infinity, it is U as well. ठीक है, the energy is U. And from in this region between X is 0 to L, the energy is 0. The potential energy is 0. ठीक है? So we want to be able to write Schrodinger equations. You're all familiar with the Schrodinger equation now, right? So we want to write the Schrodinger equation for these. For now, we will forget about the infinite square well because we have already done that before. Do all of you remember the infinite square well? We have already done that in the previous PowerPoint. So now we want to solve for the Schrodinger
Ma'am,
equation. So yeah,
ma'am, why we are studying tension when here?
because this is part of quantum mechanics. Now quantum mechanics, we have particles that can face certain potentials. So they can face an infinite potential well, they can face a potential well, and they're basically bound. We talk about particles that are facing like some situations where there's some given potential energy, right? And we want to write down the Schrodinger equation for those potentials, and we want to find what our goal is that when we write a Schrodinger equation for a particular region, there are three regions here. This is region number 1, this is region number 2. Basically, our goal is that we want to find the wave function that corresponds to the particle, ठीक है? For 3 different regions. We want to find the Schrodinger, write down the Schrodinger equation, and after that we want to solve the Schrodinger equation to be able to write our psi that corresponds to the particle. And also, for example, also we might be interested in the energies, right? That's our goal always. Our goal in quantum mechanics for these potential wells, ठीक है, is that we want to always find the psi, the wave function that corresponds to the particle, and we want to find the energies that correspond to the wave function, that correspond to the particle for the particular wave functions, ठीक है? Is that making sense?
Yes, ma'am.
ठीक है? So now our Schrodinger equation is minus h bar over 2m del square psi by del x squared, ठीक है? Plus what will it be? Plus v of psi. So it depends on the region we are interested in now. And for regions 1 and 2, we know that our energy is u. So it will be plus u psi is equals to e of psi. And we're talking about the time-independent Schrodinger equation for now, ठीक है? Because these potentials are not varying with time, and so we're not going to consider the time-dependent Schrodinger equation for now. So if we rearrange the equation, we will get d squared psi by dx squared, ठीक है? Plus, is this the plus over here? E, wait a minute. Shouldn't this be plus E minus U? Yeah, because there was a minus sign here now, so we get rid of that sign here. And then we write here E minus U psi. But this is also multiplied by, there's also a factor over here of, ये हम पहले लिखना चाहिए था. Okay, so 2m over h bar square, और यहाँ पे क्या आ जाएगा, यहाँ पे psi आएगा is equals to 0. Now we have another differential equation. ठीक है, ये इक्वेशन ये वाली इक्वेशन हो गई. यहाँ पे कुछ प्लस माइनस नहीं नजर आ रहा. I don't know why it does not come in the image, but this equation over here is basically this equation.
I think ये प्लस है.
ये प्लस ही है यार, ये प्लस है और ये वाला माइनस है. ठीक है,
ये मैम श्रोडिंगर टाइम डिपेंडेंट इक्वेशन नहीं है.
नहीं ये टाइम इंडिपेंडेंट है ना.
हाँ,
Time independent. ठीक है, it's not depending on time. So this is our equation that we have now. This is for regions 1 and regions 3. ठीक है, so now we can rewrite it in a convenient form. We can write it as d squared psi dx squared minus a squared psi is equals to 0, where a is what? A is 2m over h bar u minus e over 2m. If we write it as a square, if we write it as minus a squared psi, then what will that be equal to? It will be equal to minus, it will be equal to square root 2m. A will be equal to square root 2m over h bar u minus e, right? If we want to write this equation in terms of this equation that we have over here, इस equation के form में अगर लिखना है तो compare करेंगे तो a is square root 2m u minus e over h bar. ठीक है? Now the solutions to this equation are what? What will be the solutions to this equation? This equation here. Now differential equations, according to differential equations, we will get psi 1 is equals to c e power ax plus d e power minus. Then for this is for the region x is less than 0. One of them is for the region x is less than 0. This one, and this one is for the region x is greater than L. Remember, I said that there are two regions here. One is region 1 here, one is region 3 here. So one is a region that x is less than 0. One is a region that x is greater than L. तो समझ में आ रहा है सबको? Yes. So we get here psi 1 and psi 3. And we want to also see that, like right now, I just mentioned that in this region psi was equals to what? C e power, let's look at the PowerPoint, it's better, it'll save us time. So in this region, we said, in this region, which is x is less than 0, we said psi 1 is c e power ax plus d e power minus ax, okay? But there is one problem with this equation is that when we put, it has to, we remember one of the properties of the wave function we said before is that it has to be finite everywhere, okay? It has to be finite everywhere it can go to infinity because the probability is also finite. So e power minus of ax, if you put, it goes to, as you put x is minus infinity, like for this region here, like if you have this box over here, this box like this, okay? So here in this region, what is it equal to? We said psi is equals to c e power ax plus d e power minus ax, ठीक है? ठीक है, हमने ये कहा है कि इस रीजन में ये होगा इसकी वैल्यू, लेकिन for this is for the region x is less than 0. X is less than 0. So, but we're saying that the condition is that psi has to be finite everywhere. So what if x goes to, what happens when you put x is equals to minus infinity? Minus infinity in this equation, Which term will go to infinity? Minus infinity, इसमें डालेंगे तो ये 0 हो जाएगा ना? यहाँ पे अगर हम माइनस इन्फिनिटी डालेंगे, e पावर माइनस इन्फिनिटी 0 होता है ना, 1 over e power infinity. But if we put minus infinity in this term, it will become d, what will it become? D e power a times infinity, right? So this is basically essentially going to infinity. And we cannot, this is not allowed because psi has been defined to be finite. Therefore, we will have to set d is equals to 0. Now we are left with only this term. We are left only with the c e power ax term. Similarly, if we look at the equation for g for the region 3, ठीक है? ये समझ में आ रहा है? समझ में आ रहा है सबको? Okay, if we look at the region number 3 now, region number 3 may we have f psi 3 is equals to f e power ax plus g e power minus f ax, ठीक है? इसमें opposite हो जाएगा कि इस situation में, now in this situation we want to see what's going to happen when x goes to positive infinity. Now, why are we doing this? Is because we're trying to find the wave functions, and it's simpler if we are able to understand what we want to find their coefficients c and d, and obviously we want a, we already know, we want to find c and d, and like obviously g and f as well. Okay, so psi 3 will be equal to what? We said is equal to, yeah, here we said it is equal to f e power a x plus g e power minus a of x. So when we put x is infinity in this equation, x is positive infinity in this equation, which term will blow up? X is positive infinity means that this term is going to blow up. So we have to set f is equals to 0 because it cannot be infinite. Okay? Infinite psi is not allowed. Okay? We cannot have an infinite psi. It cannot go to infinity. But when we put x is infinity, positive infinity, into this equation, it will blow up this term. It will go to infinity. So we have to set f is equals to 0. On the other hand, इस term में अगर हम positive infinity डालेंगे, x is positive infinity, it will not blow up. So it's fine. We can leave it that way. So basically now we have psi 1 is c e power ax and psi 3 is g e power minus of ax. Okay? Now this is what we have so far. What about the region inside the well? What about the region inside the well? वो क्या होगा?
मैम उधर पार्टिकल फ्री होगा ना?
उधर particle will not be facing any potential. ठीक है? So we will write the Schrodinger equation for that region. H bar square. We've already solved this before in the previous part. 2m in the previous particle in a box in the infinite square. Well, I think we already solved this. So d square psi, yes, particle will be free because it does not face any potential there. So d psi by dx plus v will be 0. So we will get is equals to e of psi. Yes, is equals to e of psi. So इस differential equation का क्या solution होगा? In ये terms हैं, ये terms इनको इधर ले जाएंगे, ठीक है? Then the solution to that differential equation that we get is this term, these terms here. In terms of a sine these terms times x plus b cos these terms times x, ठीक है? And what are these terms here? These terms over here, we can represent this, we can write this differential equation in another form. Just rearrange the terms in the equation, right? Just rearrange the terms in the equation. Yes? Is equals to minus, or you can write it as plus 2m e over h bar squared psi, right? ऐसे ऐसे लिख सकते हैं ना हम, is equals to 0. ठीक है? So you can write this as, so this is our differential equation, ठीक है? So basically the solution to the differential equation is distinct again. And from here, what we're saying is that when b is equals to, we have to now check the boundary conditions. What do we mean by boundary conditions? As we said before, that here when x is equals to 0, now we've already defined our psi for the region x is less than 0 and for the region x is greater than L. This is for the region x is between 0 and L. So now it has to obey, these three sides have to obey the boundary conditions, okay? That means that if psi is 0, then x will be 0. Wait a minute. What are our boundary conditions in our situation? Yeah, this was for the infinite square well. For our situation, at x is equals to 0, psi 1 will be equal to c, right? Because in this region for x is less than 0, we obtained our psi 1, which is equals to c e power ax, right? This is the psi that we obtained for the region that x is less than 0. So the boundary condition, so when we put x is equal to 0, it must be equal to the psi that is satisfied by this equation in this region when x is also 0. Is this making sense? So c, obviously e power 0 is 1. So is this making sense to everyone? That psi 2 is c at 0 and psi 2 is g at L is equals to L. X is equals to L. Why is it g though? So basically, okay, but what I'm basically saying is that we're not going to solve the solution to these finite square well and the infinite square well. They will be in the more detailed quantum mechanics course. And up till here, यहाँ पे मैं आपसे like even in the modern physics book, up till here वो यहाँ तक deal करते हैं हम. And basically, yes, we will continue this tomorrow. And it's basically saying that for a solution, if you want to find the solution of these A, B, C, and G, जो कि हमने नहीं find किया अभी तक, we have to apply boundary conditions, ठीक है? जो मैंने पहले भी or psi has to be continuous at x is 0 and x is L, and d psi by dx must also be continuous. However, we're not going to do that in this course, okay? It's going beyond our course because we will be doing that more in a quantum mechanics course, okay? It's not even in the modern physics book, okay? That means that you just up till here, you just finite square well, have finite potential well. We will just do up till here for this topic. And you can just mention that if you solve up till here, it's fine, and then you can mention that we will use the boundary conditions of psi and d psi by dx. They should both be continuous at x is 0 and x is equals to L, and that's how we find the values of the A, B, C, and G, and from those conditions we will also find their values for the energy. But that's going to be more into the quantum, that will go into much more detail, and that much detail is not in this course. Okay? समझ में आ गया? And then next tomorrow we will finish this quantum mechanics course. We will just do this harmonic oscillator a bit. Okay? It's also not that much detail, but we will finish the quantum mechanics and then we will start the next topic, which is atomic structure, our next chapter. Any questions? Let me download the attendance sheet. Yes?
आप ये स्लाइड्स कब से
ये slides मैंने share तो कर लिए हैं already. Oh yes. These slides I have not shared yet. These I will share now. ठीक है, मैं अभी upload करती हूँ these slides. ठीक है? Any other questions? So I will upload these slides, in the files, class materials, load. Okay, I will do that as soon as we finish this class, okay? So did everyone understand everything that we have studied today? Was it clear? Not clear or clear?
मैम
Yes?
मैम एक चीज समझ नहीं आई
Yes?
मैम जो हमने जो फंक्शन डिफाइन किया था कि
हाँ.
3 लेवल्स डिफाइन किए थे ना एक psi 1 psi 2 और psi
Just
3
let me share the screen again. Just let me share the screen again so that is it shared? I mean, can you see what I'm posting? Can you see this PowerPoint?
yes ma'am
Okay, then it's fine. Yeah, the size that you were talking about.
psi 1 psi 2 psi 3 3 regions थे ना
Those ones. Okay, yeah, 3 regions.
yes ma'am मैम ये मैं पूछ रहा था कि मतलब आप किसी तरह x0 xl पे कुछ निकाल रहे थी साई की वैल्यू मैं सिर्फ ये पूछना था कि मतलब जो रेंज है उसकी साई 1 की उसमें 0 इंक्लूड है या साई 2 में 0 इंक्लूड है 0 किस में इंक्लूड
है zero is just at the boundary, ठीक है? Boundary conditions, it has to fulfill the boundary conditions. मतलब के psi 1 अगर psi 1 है for the region 1, it has to be it has to be continuous. Psi will always be continuous, so it will take the same value as psi 2 will take as x is 0. ये 0 included है.
अच्छा
ठीक है? Any other questions?
मैम दोनों में इंक्लूड है साई 1 में भी इंक्लूड है साई 2 में भी इंक्लूड है
Yes, that's why we have boundary condition. Means that at the boundary it should be equal to the value of psi 1 when x is 0 and the value of psi 2 when x is 0.
ठीक है
That's the boundary condition. And similar is the situation for psi 3 and psi 2 when x is equals to L. They should both be equal to each other. But it's much more, and it goes, this course is not so much all about quantum mechanics, so we're not going to go into, I will just test you up till here. I mean, agar kuch, वैसे तो finite potential well is important, but the book doesn't go into that much detail, and this is more goes into the scope of quantum mechanics course, ठीक है? Quantum mechanics course maybe would actually go and to solve the different values that we will get for these when we put the boundary conditions in there, ठीक है? We have to divide it into bound states and scattering states, and that's actually much longer than what we have over here. So then tomorrow's lecture we will do harmonic oscillator, and that's not very long either. That's not very long either. And then after that we will go and we will start the next chapter for this course. We have atomic structure. We also have particle properties of waves, and we have 2 chapters of nuclear. So we have to go a bit faster, I guess. Yeah, any other questions? Okay, no more questions?
No, ma'am.
Okay. Okay, then yeah, then we'll continue tomorrow at 3 o'clock. Okay, and by the way, our Thursday's lecture has been shifted to Wednesday, if you all know. Yes, Thursday's
Yes,
lecture
ma'am.
has been shifted to Wednesday. Okay. Okay,
Yes,
that's
ma'am,
all for today. Okay.
Office, ma'am.
Office.
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 Ma'am, you're not in your office, right?